In this video lecture, we are going to see about image restoration. I am Dr. Inbamalar, working as professor in the Department of Electronics and Communication Engineering, RMK College of Engineering and Technology. So, first let us see what is image restoration. The principal goal of restoration technique is to improve an image in some predefined sense. So this is the actual definition for image restoration. So before going to image restoration, let us just remember how the image is captured. So fundamentally you need to transfer some energy and it has to fall on the scene to be viewed. So some of the energy may transmitted, some of the energy may reflected, some of the energy may absorbed, and there is a mechanism to capture the energy back. So this captured energy will be converted to electrical energy with the help of sensors, and this electrical energy in turn converted to digital. So the techniques what we study here is digital image processing, and finally the image is in the form of a digital values, and when we process the image, it will be stored as a matrix in the processor. So the processing involves processing a matrix. Now, in all the image processing techniques, the first step will be pre-processing, then image enhancement or restoration. And let us understand both image enhancement and image restoration do the same task. So, although there are areas of overlap, image enhancement is largely a subjective process while image restoration is objective process. So let us see in detail this concept. When you have an image and when you apply enhancement technique, there is no mathematical models or rules. So you'll be operating on the pixel intensity and you'll be having the enhanced version of the image, and the user will be deciding about the quality of the image. So the user, in the sense, the subject is deciding the quality of the image and the subject is finalizing the technique without any mathematical background. So it is called a subjective process. Now, so image enhancement also gives an output, that is converts the original image into a form suitable for further processing or which is visually appealing. The same task is what image restoration also do, but here we have some mathematical concept or some mathematical background based on which the techniques are applied. So this is called the objective process. So image restoration attempts to recover an image that has been degraded by using a priori knowledge of the degradation phenomenon. So actually I have told you in the beginning about the image capturing and converting that analog image into digital image. So now you can understand there is a sensor and allied electronic circuitry, for example analog to digital converters. So some components are involved, some circuits are involved while capturing the image. So there may be some distortion or degradation of the image because of this electronic circuitry. The other thing is, during capturing there will be a sensor or a camera. Now the scene under view may move or the camera may move. So this motion will give rise to some noise. So like this, there are various parameters which degrade the image, which introduce distortion. Thereby the image is degraded. So now in the case of image enhancement, whatever is the degradation, mathematically it is not analyzed. Now coming to restoration, based on the a priori knowledge of the degradation phenomenon, we will use the techniques to restore the image. So restoration techniques are oriented toward modeling the degradation and applying the inverse process in order to recover the original image. So we are going to see the image degradation model. So coming to this techniques, we consider linear space invariant system. That means the restoration models that we consider are linear space invariant. So now with this background, let us move to the image degradation model or a model of the image restoration process. So all of us know the image is represented by f of x comma y, where x, y are the spatial coordinates and f is the intensity. So let us consider f of x comma y be the input image, and as we discussed already, the image undergoes distortion, which means the image gets degraded. So let us assume the input image f of x comma y, due to unwanted noise term which gets added with the original image, degraded the image f of x comma y into another form. Let me denote it by g of x comma y. Now given g of x comma y, that is available images g of x comma y, which is a distorted version of f of x comma y. And now we have some knowledge about the degradation function. For convenience, let us denote the degradation function using the alphabet H. And there is some noise introduced, and mathematically let us assume the noise is a additive term, and let us denote it as n of x comma y. Now the objective of restoration is to obtain the estimate of the original image f of x comma y. So f of x comma y degraded to g of x comma y. So available is g of x comma y. From g of x comma y, we are going to estimate f of x comma y. So let me denote it as f dash of x comma y. And the requirement is the estimate f dash of x comma y should be as close as possible to the original image f of x comma y. So now let me show you the model. So you see the figure. This is actually a block diagram representation of the image restoration model. See, the input image is f of x comma y, and the degradation is by a factor h. That's what we represented, degradation function h. Now this is getting added with the noise n of x comma y. So now g of x comma y is the degraded signal which is applied to the restoration filter, which is estimating the original f of x comma y. Since it is the estimate, it is f dash of x comma y. So the model consists of two segments. The first segment is degradation and the second segment is restoration. So now let us explain this process in both time domain and frequency domain. So if you consider the time domain, we know this is a linear shift invariant system f of x comma y is the input, the degradation function h. So I can consider this h as the impulse response of the degrading system. So what will happen? This f of x comma y get convolved with the degradation function h of x comma y. So the degraded image will be f of x comma y convolution h of x comma y. It gets added with the noise n of x comma y, that is equal to your g of x comma y. You see, g of x comma y is equal to f of x comma y convolution h of x comma y plus n of x comma y. So this is the spatial representation of degradation function if h is the linear position invariant operator. So representation in spatial domain we completed. Now the same we are going to represent in frequency domain. So we know that the convolution in spatial domain is equal to multiplication in frequency domain. So straight away from this equation we can write x, y spatial coordinates becomes frequency coordinates. So let me assume the frequency coordinates as u comma v. So now g of x comma y on conversion to frequency domain becomes g of u comma v. H of x comma y will be h of u comma v. F of x comma y will be f of u comma v. Convolution becomes multiplication. So this term h convolution f becomes h into f plus noise n of x comma y becomes n of u comma y. So normally it is the practice to represent Fourier transform in capital letters. So we have seen the model of the image degradation or restoration process. So when we have the knowledge of the degradation function, it is easy to appropriately choose the restoration technique. So that is the purpose of this model. Thank you.